Find the work done by the gradient vector field of f of xy equals x plus y quantity squared on a path traversing the top half of the unit circle in a counterclockwise direction. Boy, I sure do like that top half of the unit circle, don't I? Find the work done. Well, here's what I know. Work is defined to be the line integral along C of my vector field dotted dr. That I have to know to start the problem, right? Which is the line integral along C of f dotted with r prime of t dt, right? That was the second. Well, actually, that was what we got after we converted the tangent thing over. This was just purely notation. So I need to know a few things. I need to know r of t, which is what draws the curve, right? And I need to know capital F vector, which is the field. Ideas? Any suggestions?
This is a unit circle. Can you draw it out?
Okay, so you want to start with trying to get r first?
Yeah.
Okay, let's try and find the vector function that draws the top half like this. And you want to go counterclockwise, right, like this? You want to start here, unit circle 1. You're going to end here at -1. Now, we've done this, I think, twice now, right? At least twice. But we always wrote it as the parametric equations. So we wrote it as like x would be, in this case, cosine t, and y would be sine t, and then we'd say t varies between 0 and pi, right? That's what we did last class. We just need to convert this over to an r of t, a vector function. So we'll just write r of t equals the x is cosine t, the y is sine t. And that should draw the circle, right? The half semicircle there? Right, there it is. We all agree that draws it? Okay, so r is taken care of. What's the field? What's the vector field? It's the gradient vector field of this. And if you did your homework, which I know all of you are doing your homework. I know that for a fact. I've been a little frustrated lately. I mean, I hate to say it. I'm kind of coming down on you all a little bit today. But I get a lot of these homework, or a lot of these questions about these take-home tests. And I'm like, have you done the homework? No. You're not, you know, I mean, you have to, not every problem's like this, but the idea is that if you do your homework, the take-homes are a lot easier because you've at least been led into it. But I don't see that happening. Okay. I'm not here to babysit, okay? What's the gradient vector field of the scalar function, f?
It's going to be a vector with partial x, partial.
That's right, good. So you're looking at, when you say gradient vector field, everyone here needs to know what that means. That means the gradient of the scalar function f, which by definition in this case is the partial of f with respect to x, partial of f with respect to y. It's only two-dimensional because, well, f is two-dimensional. This gradient vector field, right, this right here, is the capital F they want us to use. So my capital F will be what? What's the partial of f with respect to x? 2 times x plus y. So you're doing like a chain rule on this. 2 has to come down, and then you do derivative of what's inside with respect to x, which is just 1. So you get that. Then partial with respect to y, same exact thing, right? There it is. You know what? I don't like my notation. I forgot something in this one right here. What did I guess I could have got away with it, but the way it was written in the previous note, what am I missing right there? F with what plugged into it? R of t. If you look in your notes, which again, I know all of you have printed out the notes and have them with you and keep them in class, and then this means I'm going to plug the vector curve into my field, right? And there's my field. Here's my curve. Here's my vector curve. So let's plug it in. I think I'm ready to set the integral up. What's my integral going to go from? What's my restriction on t? 0 to pi? All right, let's take my curve and plug it in to this. That means I'm going to replace every x with cosine t, every y with sine t. So this is going to become the vector 2 cosine t plus sine t. Then same thing, right? 2 cosine t plus sine t. That's the first vector. I'm dotting that with the derivative of my curve. Now, the derivative of the curve, I hadn't written that down, but I'll do it right here. What's the derivative of that curve function? How do you take the derivative of a vector function? Component by component, right? So what is the derivative of my, what was the x component of my r? Cosine t, so derivative of that? Negative sine t. And then the y component was sine t, so derivative of that is cosine t. Y'all know what I'm doing there? That's going to be dotted here. That's what's going right here. So that is negative sine t, cosine t. And finally, dt. When you take the dot product to two vectors, you get a scalar, right? Or in this case, we're going to get a function, but it's going to be a scalar function. The point being that when you dot product two vectors, you don't get a vector. So I have this now. Integral 0 to pi. And dot products, those were pretty easy, weren't they? You just do first component times first component plus second component times second component. So let me do that. How about I do this? I'll make it negative 2 sine t. That's the 2 times the negative sine t. And then I'm going to distribute it through. So cosine t and then negative 2, what? Sine squared t. That's what you get when you multiply this one times this. And then when I do this one times this, I get plus or minus? Plus 2 cosine squared t. And then plus 2 cosine t sine t. Yeah? dt. Does anything good happen here? You can take a 2 out. Yep, you can. I see that. Do you see that? It's gone right there. Unfortunately, that's not a Pythagorean identity, right? Okay, so I can do this. Let me take a 2 out. Integral 0 to pi. And if I took a positive 2 out, these would flip places and be cosine squared t minus sine squared t dt. Which what? Is that double angle cosine? I'm just wondering how many of you are comfortable with that being double angle. Most students are familiar with this one. I hope. right? That's one that a lot of us kind of got memorized by now. But for cosine 2t, there's 3 of them that you could use. What's one of them? Cosine squared t minus sine squared t. What's another one? 1 minus 2 sine squared t. That? So where are those? If you don't know those, where are they? They should be on your formula sheets, right? Not that one, though. Yeah, not that one. The ones that you're allowed to have for the class. It's the pre-cal, one of the first pages on there. So if we believe this, then that right there is cosine 2t, which is 2 integral 0 to pi cosine 2t dt. Antiderivative of cosine is sine, but then we have to scale out because we got a 2 in there, so 1/2, right? But then the 1/2 and the 2 out there are going to go away. So this is just sine 2t, isn't it? It's the antiderivative? 0 pi. Sine of 2 pi is 0. Sine of 0 is, oh man. We did 0 work. Now, I know that's all for nothing, okay, but the value of the problem was not in the fact that we got an answer of 0. If you look at the geometry of the problem, okay, the vector field is drawn here for you. And we're moving along this unit circle in the counterclockwise direction. Just take note of, as we move this around, right now, is my work positive or negative? It's a dot product between these two vectors, right? Dot products are always positive if the angle between your two vectors is less than pi over 2 or less than 90 degrees. So you can tell from this that I've got less than 90 degrees. So I'm getting positive work here, right? This is all positive work. And then as I move around and I get over to about right there, now it's opened up, hasn't it? Now I'm getting negative work. And then over here I've got positive work again. So what we have total, like a total work, right, would be 0. So what might make this problem a little more interesting is to maybe only go from this part to here, right? And all that would change is we would go from 0 to what? Pi over 2, and then we'd do all the work, everything else would be the same. So we'd be integrating 2 cosine 2t dt, and so we'd be doing sine 2t 0 to pi over 2. We already know that when we plug in 0, we get 0, but when we plug in pi over 2, what do we get? We get 0 again. Okay, so what does that mean? We plug in, we get 0 again? Does that look right? Did we have negative work back there? Let's see. This was positive work, right? Get over here. And right about past there, we get we start getting negative work. So they're canceling. So maybe we can do pi over 4, right? and we're going to get some work in here. So we do pi over 4. Right? And now that's what? Pi over 2. Sine of pi over 2 is 1, so you'd get 1. Right? The idea is that you're getting positive work and negative work together here. At the end, it turned out to be 0, but that doesn't mean no work was ever done. Yes?
Could you also represent that like how a sine wave goes up and down over above the x-axis, like as a wave?
Oh, yeah, absolutely. Look, I mean, if you really want to look at it, sine 2t, right, is a sine curve but compressed into, so it's basically, I'm going to go like that. That's a full period in pi. So if you wanted to, you could graph that as your work.
That looks a lot more.
So now you can see, like, where did you have positive work? Between 0 and pi over 2? and then hold on.
Power 4 and then.
Yeah, pi over 4, right there. There it was. This was pi over 4. So we were getting positive work at pi over 4. We got 1. Anywhere before pi over 4, we had positive work. Once we get past pi over 4, we still have positive work, but it's coming down because we're starting to add negative work to this. And then it gets to 0, and then we come back. So, okay. Find, this time, it doesn't say find the work, right? But doesn't that represent work? Doesn't this right here represent work? So if this was a vector field, and this was a particle moving in that vector field, then this would be the work done. But that's not what they're telling you. They're just saying, hey, find the line integral over this vector field. So strictly by definition, this is equal to the vector field evaluated at the vector function r of t dotted with the derivative of r of t with respect to t. And you know what? I'll leave it as c here, even though it's not great notation. We need to figure out what our limits of integration are. But I will find that out once I investigate what r is. So r is this curve. It's the parabola y equals 1 plus x squared, which I think we're comfortable with what that looks like. X, y equals 1 plus x squared. But I need to write that as a vector function. And I'm only supposed to go between -1, 2, which is here, so I need to cut that off. And I'm supposed to go to 1, 2, which is here, cut that off. Right? And I'm supposed to go in this direction. So can you draw me that parabola with the vector function? Maybe I can help. Can you draw it with parametric equations? Okay, how would you do it? X is what? T, because x is free, right? Y depends on t, on x. So x here can be whatever you want. So we make that the t. And then the y is exactly this rewritten with x replaced with t. So 1 plus t squared. This is how I was telling you last class. You could use your calculator to graph every function you've ever graphed before. What are my restrictions on t? -1 to 1, because the restrictions on t are the same as the restrictions on x. And if I start at t being -1, I'll be back here. And as I move through to t is 1, I will move along the curve, and I will come this direction. Now, that's it as parametric. To write it in vector form, all we do is just throw those equations into here. So t, 1 plus t squared. We're going to need the derivative, aren't we? Now that we're kind of getting an idea of what we're going to have to do, I need the derivative, so let's go ahead and grab that while I'm here. This is 1 plus 2t. I think I have everything I need.